In the binomial distribution in the previous lesson, we consider what we call as Bernoulli trials, where each trial has equal success probability, that the random variable takes discrete values. So it can have one success, two success, and so on. So is it possible the random variables to be continuous other than discrete? This means any number. Can we use binomial distribution for the continuous random variables? So we will look into this in this lesson. The continuous distribution. Hi, my name is Dr. Kat. I will conduct this lesson so that we can be able to differentiate between probability density function PDF and cumulative distribution function CDF. So let us get know about continuous random variables, or we can abbreviate it as CRV. Okay, random variable X could be the lifetime for a LED. Okay, in the previous lesson, we considered X, for example, the occurrence of head, the occurrence of phase 1 of a dice. But if we want to represent a lifetime of LED, for example, how long a certain LED in, for example, in this screen, LED television, for example, how long each LED can sustain. So what is the lifetime of each LED? So in this case, it is more convenient and more accurate to use continuous random variable instead of discrete as in the previous lesson. So we have a continuous random variable to represent such a quantity. Okay, compared to a countable list of values in discrete random variables, so in the previous lesson we learned about it, we can have a continuous random variables which can take any number. So not only 1, 2, 3, 3 failures, 4 failures, but in 4 success, 3 success, and so on. Here we can have any number, 3 hours. So for example, of a continuous random variable is time taken for a durian to fully ripe. It takes 5 days, 5.5 days. Okay, or a weight of a student can have a 45 kilogram, 45.1, 45.2. Okay, at the height of students, 163 centimeter, 164. So it can take any number. Exam score also can have any number. So it is not a particular number. It's not a round number which is used for the discrete variable. So we can have any number which is represented by continuous random variable. So the probability, so the function which represent that kind of continuous variable is called probability density function. So in a previous lesson, for a discrete random variable, we may write sequence of probability as this is the elements, right? The elements of the probability can have P1, P2, P3, P4, and how many trials that we have. So for sorry, this is wrong. For a continuous random, so CRV lah. So let's take CRV. For a CRV, we define a probability density function over negative infinity to infinity, having the following properties. So the probability, the PDF, we can say the PDF must be larger than 0 for the range of negative infinity to positive infinity. And if we take the area under the graph of the probability density function, we get it is equal to 1. And for any two variables value, such that it is between infinity and positive infinity, so we can calculate the probability for that interval to occur by having the definite integrals from that two conditions and integrate it over dx. Okay, so unlike pi, so this is pi, pi is a probability, for that thing to occur, but fx is not directly, is not probability. It is related to probability, but it is not probability. Fx is not a probability. Okay, so these are the difference between the binomial. In the previous lesson, we learned about the binomial distribution and the continuous probability density distribution. So in the previous binomial distribution, we have discrete values, but for continuous probability distribution, so we can have any number. So it is continuous number, it can have any number. So that is the difference, even though the shape look similar. Okay, and then let's go to the cumulative distribution function. So the cumulative distribution function, so this is the probability function. Okay, so the probability of the cumulative distribution is the accumulation of probability value. Okay, so for example here, so when we calculate the probability, which is the area under graph. Okay, so the probability is the area under graph, yeah. So the probability is area under graph. Okay, area under graph. Sorry, fx. Okay, so the probability of a random variables is equal to area under graph. So you can see this is increasing. Okay, and then when we add up, okay, so it is it keep going, so until the end. Okay, if we get actually the property of the distribution function is that the area under the graph must be equal to 1. Okay, so it will approach to 1. Okay, so this is the accumulative probability. Alright, so this corresponds to the value here. Okay, so it is the probability start from 0 and it accumulates for each x value until it reach 1. Okay, so from here we can see that fx almost equal to 1 as x equal to infinity. And then the probability for given under between two area here is the actually just the definite integrals between two border here, and which is also equal to whatever from here, so the minus whatever here. Okay, right, so this minus this one, minus this one. Okay, okay, all right, next. So for example, let x the random variable of time to failure of LED measured from time t equal to 0. So assume that the function, the probability distribution function of that LED is given by this, where you can actually from here we can draw this is exponential, right? So it is start from here and it is going to 0 but not 0. Okay, right, so this is alpha exponential minus alpha t. Okay, it start from 0. Okay, what is the probability that the LED fails between 10 to 20 hours? That means maybe somewhere here. Okay, in this is x, or better we put it t. So this is t, this is t, this is t. So maybe this is 10 and 20. Okay, so what we want to calculate is the area here. The area here under the graph. Okay, so what we can do is that you find the definite integrals between these two value. So 10 to 20, so you can calculate this is the definite integral, so you get the probability is equal to this, where this alpha is left as an unknown. Okay, for the probability distribution, the accumulative distribution, we can have actually it is all about like this. Okay, so this is one. Okay, so is something like this. Okay, this is the accumulative probability distribution. Okay, so similar to the discrete binomial distribution, it also have a mean and variance of continuous x. So let's compare. This is for binomial and this is for continuous random variables. So you can see there is almost similar, except that this is the summation because it is discrete, and this one is a integral because it's continuous. Okay, and then you see that this is x multiplied by probability distribution function. This is the probability times the x. Okay, and also for the variance, it is also similar like this, so you can compare with this. This is the x minus the mean. Okay, so mean is can be calculated from here. Okay, so you can have a similar mathematical way, except that for continuous we use integration. For this we use the summation. So this can be also seen from the again the distribution between these two. You see this is a discrete, this is continuous. So the nature is almost the same, but the mathematical method is just a little bit different. All right, so in the next lesson, we look into the teaser again. Is it possible? Okay, so is it possible? Yes, right? This is also yes. Okay, so that means we can have other than discrete, we can also have a continuous variable. Okay, in the next lesson we will go into the special case of continuous distribution called a normal distribution. Okay, then bye.